Okay, hello everyone. Let's give a few more minutes to see if everyone else joins, if anyone else joins, and then we can start. Okay, I guess we can start. So to start with, a few of you told me that like the office hours don't work for you and like because you're at work. So I'm thinking about doing this thing like where I will do like office hours by appointment. So you guys can send me an email whenever you have some issue or questions that you want to discuss with me, and then we can set up a time together that works for both of us, and then we can like have the meeting then. How does that sound for you guys?
Sorry, I just joined. What did I miss?
Yeah, so I was saying like a few of you told me that the office hours don't work for you just before this class. So I was thinking like we can do an office hour by appointment where you guys can send me an email whenever you have something to discuss, and then we can set up something within the next couple of days, a time that works for both of us, instead of this office hours.
That works for me.
Okay, sounds good. Yeah, we can do that then. Okay. So moving on, let's see. So I have got the project suggestions from most of you. I'll like try to set up the poll within this weekend, and then we can have the voting, and then we can have hopefully the formation of the groups by our next class, and we can start working on the projects. So I'll do that this weekend. I'll find a final list of topics, and then I'll give it up to you guys to, vote on which project you want to work on. Um, okay. So that is one thing. Let me see. Okay. So for this week, let me share the screen. Okay. Okay. Let's see. Yeah. So for this week, we have our module 3 overview, which is what we are going to do this week. So we already previously learned application layer, the principles of network application, the web, HTTP, and also email, and the protocols that were associated with email, like SMTP, POP, and IMAP. So for this week, we have a few videos that we can watch, which a few of them are on client server and P2P networks that we had covered, and then some details into some of the topics we're going to cover today. So for the quiz that you have due is actually based on what we did last class, which is 2.1, 2.2, and 2.3. And then for the next quiz, I'll consolidate whatever we teach in this class and some of the next lectures. So yeah, so I put this here because this is these are the only three sections that you will have to read for this quiz. So for most of the modules, like for all of the modules almost, so the read that you see here is the part that will be in your quiz, like that will be covered in your quiz. Sorry about that. Okay. So we have a discussion board as well this week. Let's see. Right. Okay, so for this discussion this week, it is about problems and solutions of peer-to-peer networks. We covered a brief overview of peer-to-peer networks in our last lecture, and we'll go over more in the next lecture. So for this, we have um, we have a document, official document, Senate session that was on the problems and solutions of peer-to-peer networks, and it has some details here mostly, and then the copyright liability that people need to have, and the suits that were filed against individuals who had peer-to-peer networks and everything. So for this, you have to read that page, the link of which is given here, and then you have to provide some evidences for and against, like limiting file sharing P2P networks, like why we should do it and like what are the benefits. So some benefits as well as some problems with peer-to-peer networks, why they should be limited. So again, this is due September 17th, which is throughout this week, and then we have so we have our first assignment for which you have, let me see, yeah, up to September 24th. So you have nearly 2 weeks to complete this. So this is based on whatever we have covered till the last lecture, which is the first chapter, like the basics of networking and all the layers, and then up to where we did on application layer in the last lecture. So there are some questions you can like write the answers up on and convert them to a PDF and then upload them here. Yeah. So this is the assignment, and this is due, like this has 2 weeks to be submitted. And then there is a lab which has 1 week to be submitted, which is on HTTP, the one we covered. So this uses Wireshark. So I believe you have already installed Wireshark due to your first lab. So this uses Wireshark, and again, it asks you to go to some websites and then test the HTTP versions from there. If for some reason you're not able to access these websites or you're not able to get the appropriate packets, you will always have the files. Let me see. Yeah, you'll always have the files zipped at the bottom. So this is the same similar packets that you will get if you go to the website. So if that doesn't work for you for any reason, you can always download these and then open this using Wireshark and then do the remaining of the question answers there. So that is also another way. So for this lab also, you need to do the initial steps of setting up everything and getting the packets. And then it asks you a bunch of questions which you have to answer as part of your lab, right? So this is the second thing, that is the lab that is due. Let's see. Okay, again, there is a quiz for this module also, which is based on what we said, like these three things. So make sure that you go over your, study materials before you attempt the quiz. Yeah, so that is it for this week, and then you have the assignment which has 2 weeks to be submitted. Let's go back to the slides now. Unless anybody has any questions, we can go back to the slides. Let's see. Share my Okay, you guys can see the screen, right? The presentation screen.
Yes.
Okay. Cool. So we covered the basics of our application layer in our last class and some of the protocols and applications that run in this layer, which is, you can say, the top layer of our network layers. That is, this is the one that is closest to the user. If I am the user, then this is the topmost layer and closest one to me. So we covered web and HTTP, which is Hypertext Transfer Protocol, which is our web protocol. We also covered email and the protocols we use in emails, which is SMTP and POP and IMAP. So now we move on to another protocol in the application layer, which is called DNS or Domain Name System. So let's go into that. So DNS stands for Domain Name System. So what does this do basically? So you know that for networks to reach from one device to another, sorry, okay. 1 second. Okay, yeah, so in order for networks to go from one place to another, we need IP addresses. Like these are like the destination addresses and the source addresses. So for example, if I write a letter to somebody, the address that I am writing from, like my physical address will be an IP address in, like, if you compare analogically, and then the person I'm sending it to, their physical address will be another IP address. So I need these two addresses in order to, like, I need the destination address in order to send my letter. And then if they reply back, they need my address as well. So these IP addresses are often like something written very numerically, like let's say 10.10.0.1. So this is how an IP address is formatted, and we will go more into details when we go to the next layer, next layer, sorry, which is the IP layer. But for now, all of the places that we can go on the internet, all they have this address, which is the IP address. But when we as a user want to go to some website or some server, we hardly remember these numbers, right? So like, I don't know what, let's say I want to go to google.com. I don't know what IP address Google has. So I, as a user, need this system where I can map the name that I know to the IP address, which the internet will use. So DNS is the protocol that does exactly that. It maps names to IP addresses. So for example, yahoo.com, it will map it to the proper IP address where yahoo.com actually exists, right? So let's look more into how DNS does that and what DNS actually is. So it is a distributed database. Firstly, we don't have one single server somewhere that has all these mappings. We have this distributed in a hierarchy of a lot of servers. We'll go into this hierarchy in the later slides. But for now, we don't have a single system that actually has all these mappings. So this is actually distributed in a kind of hierarchy. And this is obviously an application layer protocol because it helps the users the most, right? It is not a protocol that the internet needs in order to do its functioning. It is something that the user needs. So this is an application layer protocol. It exists in the application layer at the end hosts. Like if I am on my laptop, this protocol would likely be operating in my laptop, not in the routers in the network, right? So hosts and name servers communicate using DNS to resolve these names to IP addresses. And this is a core internet function. Obviously, we need it because not like no human being can, memorize all these numerical IP addresses or write it down somewhere. So this indeed is a core network function, but it is implemented as an application layer protocol. So what happens? It exists at the end system. So that is why we call it like complexity at the network's edge. So when internet has this basic philosophy, or most of the systems actually have this philosophy, when they are a very structured and what do you call it, expandable system, we try to keep all the complexity at the edge. so that the central network is free of complexity and can do its task very efficiently, like with less complexity. So any kind of complexity we want to do, we try to push it towards the edge. So that is why we have DNS, which is a complex protocol, and we have it towards the edge of this network, that is in the end systems or in the hosts. So what services does DNS provide us? Host name to IP address translation, like we discussed. So it can translate any host name like google.com, yahoo.com, facebook.com, instagram.com, anything to an IP address, or even gmail.com, like Gmails. So it will translate a host name to the appropriate IP address. What else does it do? It also does host aliasing. So I'll give an example of host aliasing. So most often www.facebook.com is not the name of the Facebook end server, right? So facebook.com is a kind of alias. So another very common example is, if you go to your browser and if you type gmail.com and press enter, it will take you to this website called mail.google.com. It will not take you to gmail.com. So gmail.com, because it is so commonly used and the popular name of the website, it is an alias of the actual or canonical name, which is mail.google.com. So DNS also translates these things. And then any kind of server aliasing, like mail server aliasing. So all of the servers also, they have a separate name for them, which is very often not what we call them. Like, for example, let's say most of the AWS websites, like if you go to their actual canonical name, it is much more complicated with the zone initials and everything. It is a big name. But you can just press like aws.com and then go to that server, like where it exists. So this is also a form of aliasing, which is called mail server aliasing. And then DNS also helps in load distribution. So what you can do is, you can host your own website. Let's call it like, let's say google.com. If you're hosting google.com, because you have so many users, you will likely have more than one servers catering to everybody, you know. So, or let's say Netflix. If you are a Netflix like host, then you will have a lot of servers at a lot of places where you have the same data, and then users who are near that server can access data from there. But since this is an internet, right, all of these servers, they will have different IP addresses that identify them distinctly within this internet. They cannot have the same IP addresses, right? Because they are different entities. But when I go to netflix.com and when I click a movie, I am redirected to my nearest server, like the server nearest to me. So what DNS is doing is, DNS is distributing the load. Like for me, when I am typing the same hostname, it is taking me to a different server with a different IP. And then if somebody is there in Australia and they are pressing netflix.com, they are going to netflix.com, DNS is taking them to the server nearest to them, thus distributing the load, right? So this is why DNS also has the function of load distribution. So why do we not centralize DNS? So anything centralized, we will have a single point of failure, and we don't want that, right? Because DNS is such a integral and fundamental component of our internet. We don't want a central point of failure. So we are not centralizing it. So and then traffic volume. So like we mentioned, we also do load distribution via DNS. So we can, if we centralize DNS, we'll have all these Netflix users going to the same server. So the same server will have a lot of traffic. So instead, what do? We have different servers and then we distribute this load using DNS. Also, if we centralize DNS and if it was, let's say, here in USA, and if somebody from Australia wanted to access this, they would have a significant delay, right? So for them, this centralized database would be distant, and that delay would count every time they are querying DNS for something. So that doesn't like work very well. And then also maintenance. If you need to change something in like in your server, you need to update it. If anything goes down, it is just that one system. So if you need to maintain it, your entire DNS service is down. So you don't want that. So we don't keep DNS as a centralized protocol. We have implemented it as a decentralized function, and we'll see how all over the globe. So it doesn't scale if it's centralized. So let's see how we have implemented DNS in a decentralized way. So this is how DNS actually is implemented on the internet. It is a hierarchical structure. So we have root DNS servers, which are like, you can say, the base DNS servers. I think there are 13 root DNS servers. We'll see which ones they are later. And then these root DNS servers contain the IP addresses or the locations for the TLD servers, which is called top level domain servers, which are these com, org, edu, .gov, what else is there? .org, and then there is maybe if you are here, it is .us. So like it can be your country's initials also. So all of these com and all these, they are called top level domain servers. So they fall under the root server. So the root server contains the IP addresses or the locations for all the top level domain servers. And then what do the top level domain servers contain? They contain the IP addresses for the servers below them, right? So these are the local servers, which are like yahoo.com, amazon.com. If you open a website tomorrow, something like, let's say, game.com, then it will fall under the com DNS server. And then the com DNS server would have the location of the IP address to your DNS server. So similarly, org will have its own org local servers. Similarly for edu, so temple will have a temple.edu DNS server below this edu DNS server, right? So what happens? So let's say you are a client, you want to find the IP to www.amazon.com. What happens? First, the client will query the root server. Do you have the IP of amazon.com? If they don't, they will ask the since this is a .com, they'll ask the com DNS server. The com DNS server will then ask the amazon.com DNS server for the IP address for www.amazon.com. And then it will be sent back to the client. So this is how it works. If somebody asks for a IP address of a specific domain, it will trickle down through the hierarchy to where it actually exists, and then it will be sent back. Like we said, we start with the root name servers, which were in our diagram the top server, right? So these are contacted by the local name server if they cannot resolve the names. Give me one second. Okay. So these root name servers, these are at the top, like we mentioned here. These are the root DNS servers. The root DNS servers will contact the servers below them for the mapping if it is already not known. And then it will return that mapping to whoever is asking for it. We have 13 logical root name servers worldwide, but these are not the only 13 that exist. They are obviously replicated many times in order to be, redundant, so that if one fails, we still have some place to ask. So these 13 are the logical root name servers, and then actually they have multiple IPs where they host the same service. We have quite a few in the US, as you can see, and then they contain the sites for some of the top level domain servers below them. Then we move on to the authoritative servers, which is called TLD. TLD is the top level domain server, which has all these .com, .org, .net, .edu. All these all these domains fall under the top level domain server. If you want to learn a bit more, then you will know that Network Solutions, they maintain the servers for the .com top level domain. EduCause maintains it for the .edu, and there are others also who maintain all these others. And all top level country domains, they also fall under this category, like .uk, .fr, .ca for Canada, .jp for Japan, like that. And then under these top level domain servers, there exists the next hierarchy, which is the authoritative DNS server. So the authoritative is where an organization's name comes into play. Like Amazon.com, Google.com, Temple.edu. So why are these also servers? Because they can have multiple domains under them, right? For example, temple.edu might have application called, let's say Canvas. Like if I open up Canvas, even though it doesn't happen, if it was a temple owned portal, it would have been like canvas.temple.edu. So now your temple.edu DNS server will have the IP for this canvas.temple.edu, and then you can have another called mail.temple.edu, and similarly your temple.edu server will have the IP for this mail.temple.edu domain website. So your organization's own servers also provide, these hostname to IP mappings for all the organization's named hosts, which are, named by your organization, and they can be maintained by organization. If I am Temple, I might maintain it, or if I am a smaller organization, they might be maintained by the service provider. Let's say Xfinity. Xfinity might maintain the server, authoritative server for my named hosts. So this is a hierarchy that forms starting with the root level domain servers, then the top level domain servers, and then we have the authoritative domain servers, right? So we also have these local DNS name servers. They ideally, like, they don't belong in this hierarchy, but you can think of them as like default name servers. Like if I make a DNS query, this query will be first sent to the local DNS server, and this DNS server is actually like not, it does not have a what do you say? It does not have a responsibility of that it has to maintain these mappings, but it is just like a cache. So what it does is, if I today ask for the mapping of google.com and I get it back from this hierarchy, right, that it is 10 dot something dot something dot something, this local DNS name server acts like a cache that will store this mapping for the time being, right? And then it will, after a certain time, it will let go of this record. But if I browsed 20 websites yesterday, then it will maybe store the name to IP mappings of all these 20 websites in its cache. And then if I ask for one again today, if it already has it in the cache, it does not need to query the whole DNS hierarchy for this IP again. It just gives it to me. So that is why this is not exactly a part of the hierarchy, in the sense that it does not have a specific responsibility of some mapping that it has to keep. It is just like a local cache, right? And because it is a cache, it may be out of date. Like if it sends me some Google IP and then the next moment Google changes, like due to some load balancing issue, the IP changes to the server that Google wants me to go to now, this might now have a out of date IP. So this acts as a proxy. If it does not have something, it will forward the query into the hierarchy and then it will store it again. So let's see an example of how this DNS name resolution works. So it works in two ways. The first we'll show is an iterated query, and then we'll also show another way it works, which is called a recursive query. So just like if you have like gone through iterative and recursive logics in programming, you might already be able to guess how this works. So let's see. So let's say this is a host called cis.poly.edu, and it wants to reach this one, gaia.cs.umass.edu. And it, let's say its local DNS server does not have the IP of this host, right? So what it does is, irrespective of everything, it will ask the local DNS server, do you know this? If you don't know this, please tell me where to find this. And then the local, so this request goes to the local DNS server, right? Which might have a host name of dns.poly.edu. And then the local DNS server, it does not have this IP to host mapping. So it sends this request to the root DNS server. What does the root DNS server do? The root DNS server, in case of an iterated query, tells it, I don't know the IP, but you know who might know? The top level domain server. So here is the IP of the top level domain server. Ask them. So then the local DNS server asks the top level DNS server that, do you know where this IP is? And then the top level DNS server does what? It says, I don't know, I don't have this, but I know who might have this. Ask the authoritative DNS server. They might have this. So then the local DNS with that IP again contacts the authoritative DNS server, and this person will have the IP of gaia.cs.umass, and they send back that IP address. So once the host has this IP address, they can now directly communicate with this device through the internet. So this device host gets back the IP address, and now they can communicate directly. So in recursive query, what happens is, just like a recursive query works, the host will ask the local DNS server, hey, get me this IP address. The local DNS server will tell the root DNS server, please get me this IP address. Instead of the root DNS server sending back the IP of the top level domain server, like we discussed previously, it will just ask the top level domain server that, hey, give me this ID, which will again trickle down the command to the authoritative DNS server, who will send back the IT to the top level DNS server, who will send the IP to the root and then to the local DNS server. So what is the negative impact of this is it puts a lot of load on the root DNS server, because as we will see later that most of the times the local DNS server, they already have most of the IPs of the top level domain server. Like they'll have the IP for .com, .edu, .gov, all those things. So they very rarely need to communicate the root DNS server for these. So this puts a lot of burden on all of these, because they have to, like, they cannot just complete it here. They have to go through the entire communication, storing their data, forwarding the data, and all this. So that is why, like, iterative queries are more preferred, and that we will and recursive queries are not that much preferred in cases of DNS name resolution. So what happens here? Any name server, they learn the mapping for the first time. Okay, this name is for this IP. They cache the mapping, right? They cache it for some time. These cache entries do have a time to live, so they will disappear after that time to live, but for the time being they'll cache it. So typically all the top limit domain servers, their IPs are cached in the local name server. So like I mentioned, all this local DNS server, they already have the IPs for all the top level domains like .com, .edu, everything, .gov, .uk. Most of this, if you have gone there, they have likely asked the root server sometime for this, and they have kept it in the cache for the time being. So they rarely have to go there. So that is what it says. Like top level domain servers typically have this local name servers IP mapping cached. So root servers are not often visited. So cached entries may indeed be out of date. Like even within the time to live period, they might have been like updated, and now whatever is there in the cache, that is no longer the accurate representation. So this is a best effort name to address translation. If it is not there, it will just fail for that, and then it will retry. So until the all the time to lives expire, then you will not know. Like for example, if I have Google's IP as this, and then it changed. Let's say it changed to a place where this IP is no longer reachable at all, like the old IP. So until all the DNS caches over the internet have expired their time to live and send out new requests, they will all have the old IP, right? So this was a problem. So that is why they created RFC 2136, which proposed how to update and or notify if some IP is updated, then how to notify the DNS and how to propagate it throughout all the DNS that, okay, this is not the IP anymore, this is the IP. That was defined in RFC 2136. So we understand what the problem was with the cached entries being out of date, and then why we needed this update and notify mechanisms, right? So DNS records. So now, obviously, DNS stores this name to IP mappings, but we need to see how they store it. Like, what is the format? So these are called resource records or RRs. They are stored as name, value, type, and time to live. So we already know the name would be the host name, and value, in most cases, it would be the IP address. We'll go into what the types are. and then TTL is the time to live, like after what time it will expire. So if the type is A, then as we know most commonly, it is a name to IP mapping, and the name is the host name, and then the IP is the value, and then we have the type as A. Now there are also types called NS, where if the type is NS, then the name is the domain, and then the value is the host name of the authoritative name server. So this, think about when you are in the top level domain DNS, right? So for a top level domain DNS server, you need to store the names of the authoritative level domain servers, right? You need to, like, if you are a .edu domain DNS server, then you need to store the records of where temple.edu is, where umass.edu is, where maryland.edu is. So all these things. So for this, the records will look like this. The name will be the domain name or temple.edu, and then the value would be the authoritative name server's name, like let's say dns.temple.edu. If I want to request IP of somewhere, something under temple.edu, which DNS server is the authoritative server, that value would be here. That would be the host name. So this is the other kind of resource record. And then the third kind we have is called CNAME, which is a canonical name record, where the name would be a alias name, let's say gmail.com, and then the value would be the actual canonical name, like google.mail.com at some server. So here, for example, they give an example where name is www.ibm.com, which is what we call it as, and then the actual IP, the actual host name, which is the canonical name, looks something like this: servereast.backup2.ibm.com. So these values are also stored in resource records, because even if you put a alias name, the DNS server has to know what you are referring to, right? So the name would be the alias name, the value would be the actual canonical name, and then there would be a type which is CNAME, and then a time to live for that as well. And then the other type would be MX, where the value is the name of the mail server associated with the name. So sometimes if you send, I don't think Temple has it, but sometimes you might want to send an email to, like, okay, let's say I want to send an email to myself, which is my Temple email ID, like my first name dot last name at temple.edu. But the actual name of the mail server that I'm sending this email to is not my first name dot last name at temple.edu. It might be my TUID at temple.edu, or it might be more complicated, some server name and some name at temple.edu. So the MXs stand for these, where the name is the one that I am sending to, like first name dot last name at temple.edu, and then the value is the actual name of the mail server that will actually, that you are sending this email to. And then the type would be MX, and then there would be a time to live for that as well. So these are four of the types of DNS records you might see when you're going into a DNS server at any of the levels. And then DNS has messages, like you can query a DNS asking what is the IP for this host name, and then the DNS sends you a reply that, okay, this is the IP for the host name that you requested. So both of these messages, to save complexity, they have the same format essentially. Like the format that is for the query is also the same format for the reply message. So what are the fields in this messages? We have identification, which is a 16-bit number that is used to identify that this is the query and this is the same reply to this query. So this is a 16-bit number which we used to identify what reply stands for what query. And then we have a lot of flags also. Like we can have a flag denoting whether this is a query or a reply. If it is a 0, then it is, let's say, a query. If it is a 1, then it's a reply. And then whether you need recursion, whether recursion is available, whether the reply is from an authoritative server. So all these kinds of flags exist. And then you can ask questions, like with the question number. These are also fields to identify, like identification. And then you have questions and answers field. So like where you ask questions about, like, this is the host name that I want it for, and then you get answers like the resource records with the name, the value, the type, and the time to live. You get all of these as a record in the answer, right? So you have the name and type fields for a query that you are sending out, and then the resource records in the response to the query. And then for authoritative servers, you get your records in this field. And then if there is any additional comment or info that the server needs to tell you, then that is used within this additional info block. Some of these blocks, the additional info blocks are just kept blank, that in future, if you need to convey some new information, some new kind of device comes, then you might use some of the blank fields in this additional info to propagate that information as well. So this is how a DNS message format looks like. So how do we insert records in a DNS the first time that we do it? So let's say I'm starting a new startup. I call it Network Utopia. I need to register this name networkutopia.com at the DNS registrar. Let's say it is Network Solutions because it is a COM server, right? So what do? We provide the name and the IP addresses of the authoritative name server. And then the registrar will insert 2 records into the server, top level domain server. What will it do? It will insert the record of the DNS server that it needs to reach. So that is networkutopia.com, dns1.networkutopia.com. And this is the address of the authoritative name server that it should go to. And then you have the actual record of the DNS name server, which is the name of the server, the IP address of the server, and this is a value, like a normal value. So what happens when we introduce these two? Now the top level domain server knows that in order to go to networkutopia.com, I need to go to this authoritative name server. And then I also know that for this authoritative name server, I have the IP address this. So we create authoritative server type A record, and then we create a NS record. This is actually a mistake. This is not MX, this is a NS record. Okay, so every aspect of the internet is very prone to attacks. So every layer you will see in the internet, every layer is prone to attacks of a different kind. So DNS is also prone to a number of attacks. So the first, which is a very, very common form of attack, is a DDoS attack, which stands for Distributed Denial of Service attack. So what is a distributed denial of service? It is basically when somebody is trying to overload a server by sending it random information, like just anything that doesn't make sense also, but the server anyways has to process it. So what happens? So the server now doesn't have bandwidth for actual real requests that come to it. So this is called a denial of service attack. And then a distributed denial of service attack is where the attacker uses a bunch of separate devices, all of them together to create requests and bombard the server. So we'll go more into that later. But so DDoS attacks happen most commonly in DNS, where people like attackers either try to bombard the root server or the top level domain server with a lot of traffic. But the root servers are not very prone to this attack because of 2 main reasons. The first reason is most traffic to the root server is very filtered because there are only a certain number of top level domain servers in the world. Like you can it is a very finite number, like .edu, .com, all the countries and their expansions, and then you have .gov. So it is a very finite list. So all the traffic to the root server has a very stringent traffic filtering where they can filter according to these top level domain server IPs. So, and most of the local DNS servers, like we mentioned, they have already in their cache the IPs of most of the top level domain servers like .com, .edu, .gov, .org. They might already have in their cache because we visit these top level domain servers very regularly. So nobody has to actually visit the root server that much. That is why it is resistant from DOS attacks a lot. But who is more prone is the top level domain servers because they do most of this heavy lifting of traffic. So when they are bombarded with DOS attacks and they don't have as much traffic filtering because most of the local servers and most of the other servers, they reach out to these servers. So a DOS attack on a top level domain server is potentially a lot more dangerous. And then we have other kinds of attacks as well. Like we have redirect attacks where somebody in the middle is intercepting these queries or doing DNS poisoning. Like let's say what I can do is I will just take this, like if somebody is asking for an IP, I will just change the IP so that now, like let's say I am looking for google.com, right? I'm asking it to the server, and then while returning to the server, somebody intercepts and changes the IP address of the Google server. Like it was 10 dot something dot something, and they change it to their own IP address. So now when I want to go to Google server, I go to their malicious website instead, and then something bad happens. So these are also forms of attacks where you do redirection or you exploit DNS. So like I mentioned, like if I am asking for a value, they can change the value when it comes back to me. Or even some attackers, what they do is they put in random like values in the DNS server itself. Instead of changing it on the way, what they do is like google.com has an IP on the DNS server as 10 dot something something. They will add a new entry where it will say now google.com has the IP 192 dot something something. So the DNS will update its record, but this new IP is not the actual Google IP. So this is called like exploiting DNS for DDoS. Now what happens is, let's say I put your IP in place of google.com's IP, right? So now everybody who is asking for google.com IP, they will get your computer's IP instead, right? So what happens is now I am not doing anything, but everybody is attacking your computer now. They are sending all their google.com search requests to your device. So I am doing a DDoS attack on you without actually having to do anything. So this is also another kind of DDoS where DNS is used to launch this DDoS attack. So these are some kinds of attacks that can happen on DNS, some potentially malicious attacks that can happen on DNS. So we can see that DNS has a lot of obviously functionality in the internet because we very rarely remember IP addresses or even have the potential to remember IP addresses. So DNS does that for us. We have to remember very user-friendly website names like Google, YouTube, temple.edu. We just have to remember them, and DNS will do the rest of the work for us. Okay. So now the next topic we'll go into is we'll go into peer-to-peer applications in more detail, right? So what is a pure peer-to-peer architecture? It is where there is no always on server, because if there is a always on server, this becomes a client server architecture. So for a peer-to-peer architecture, I'm also a peer. I don't need to be always on. You are also a peer. You don't need to be always on. So these are arbitrary end systems that communicate directly instead of having to go through any server. These are peers that are intermittently connected. Like if I am sending a file to you, we are connected now and then we are not connected anymore. So they are intermittently connected and they change IP addresses. If I have a cell phone, I am at home, my IP address is within the domain of my home network. So it is something. If tomorrow I go to Temple University and I connect to their Wi-Fi, I might have a different IP address. So these peers are intermittently connected and they keep changing their IP addresses. So some of the most common examples of P2P architecture, the first is file distribution via BitTorrent. We all probably know of torrents, right? So this is a very, like this was a very famous file distribution site and it worked using a very efficient peer-to-peer architecture, as we will see in a bit, but it was a very efficient peer-to-peer architecture. Some of the streaming websites, I think CanCan is a Chinese streaming website, I think, if I'm not wrong. So they also did video and movie streaming using peer-to-peer architecture. Similarly, Skype has also a proprietary protocol that uses peer-to-peer architecture in order to, do phone calls and like phone calls, like voice over IP. So now let's see how it works. So first, why peer-to-peer, right? Why do we need peer-to-peer if we have client-server architecture already? So let's see this question. How much time to distribute a file of size f from one server to n other peers, let's say n clients for this case. So now what are the criteria? So we have the server upload capacity as US, we have our file size f, and then we have our n number of hosts that want to download this file, each with a download capacity di and upload capacity ui, right? And let's, for this example, consider that this network has abundant bandwidth. We don't have any bandwidth restriction of any kind. So this is the situation we are dealing with. So what happens now, in order to send this file f to all the n hosts or all the n clients, we must sequentially, if we are doing a client server architecture, we must send this file n times, right? I send to U1, the first client first, I send to the second client next, and I have to send, like, I have to do a client server connection every time, and I have to send this file, and then I have to set up client server connection with the other one. So I have to do this n times in order to send the file f to these n clients. So time to send one copy would be the file size by this upload capacity, which is f by us. And so the time to send n copies would be n times f by us. So now the server has uploaded this and the client has to download it, right? So each client must download one file copy. So let's say d minimum is the minimum client download rate, like the client that is the slowest in downloading the file, that is d minimum. So the minimum client download time would be f by d minimum. So what do we get? The time to distribute this f file to all the n clients using this client server approach would be greater than or equal to the maximum among either the file upload time, total file upload time, or like the slowest file download time. Whichever of them is more, it will be that value, or it will be at least more than that value. So this is when we are doing client server. Now what changes when we do a peer-to-peer architecture? Let's see. So this will increase linearly in n, right? If n, the number of clients you want to send the file to increases, this value will also increase linearly. So now we go into peer-to-peer architecture. So what happens? Now the server, if you remember, like in peer-to-peer architecture, everybody is both a client and a server, right? So everybody has the capacity to share whatever they have got from the other person. So this time the server has to only upload one copy of the entire file, the F file. It just has to upload once to the network, which takes time, F by US. And each client, they have to download this file once, which as the previous time is f by d minimum, the minimum client download time. Now all these clients, once they get some part of the file uploaded, they can share this file to other clients. We'll see how that occurs, but every host here, they can also act as a server and they can also send part of the file to the other people. So since we know all of these have upload capacity as UI, the maximum upload rate for this network would be the upload capacity of the server US plus the summation of the upload capacity of all these n hosts, which is summation of UI. So this time, the time to distribute this file F using this approach would be the maximum again. In between this, time to upload one copy by the server, time to download the file by the slowest server, and n times, that is because there are n clients, the file by this upload capacity of the entire network working as a peer-to-peer system. So whichever one is the maximum of this, that is the time to distribute. So what happens here? We know that n, because if we increase the number of clients, this n will increase linearly, but this upload capacity will also increase linearly, which is the main advantage of a peer-to-peer system, that every system that joins the network also brings with it some capacity to work as a server. So think, every device you are adding to a peer-to-peer network, now you get both one client and one server in your client to server network. So it kind of balances it out. You get more server capacity also, because these devices, They work as servers also. So this is why peer-to-peer has a faster file distribution time when compared to a client server architecture, a much faster file distribution time actually. So we can see that when we increase the number of n, if you have a client server architecture, the minimum distribution time will increase pretty much linearly. But if you have a peer-to-peer architecture, this is not very linear at all, right? This will as like when you increase the number of n to a certain extent, it becomes almost parallel, right? It starts going almost parallel to this axis. So what this theoretically tells you is that once you add more than enough devices to your peer-to-peer network, your minimum distribution time remains the same. It doesn't increase anymore. So within the same time, you can now distribute files among as many people as you want. So this is how it is more advantageous when the number of n increases. So how does this work, right? We all must be very interested to know now. This seems pretty advantageous, but how does it work in reality? So let's say we have a file which is now divided into 256 kilobyte chunks in order to be sent over the network. So let's say this file is divided into 256 kilobyte packets, like each packet is, it is not, but let's say like this is divided into this size of chunks. And there are all these peers that are existing in this network in order to send or receive these chunks, right? And then we always have a tracker server who keeps tracks of the peers which are in the network. So now what happens? So this group of peers, they are called a torrent. So now let's say Alice arrives. Alice wants to download this file from this torrent, right? That exists, that is divided into 256 kilobyte chunks. Alice wants to download this file. So from the tracker, Alice will obtain the list of the peers that are already existing in this torrent. So that these are the devices that she can get the file from. So Alice now begins exchanging file chunks with the peers in the torrent. So Alice will ask some of them to give Alice some of the chunks of the file that they already have. What happens? Peer, when they are joining torrent, they have no chunk from the file, they are just starting, but they will start accumulating them over time from the other peers. So they register with the tracker to get the list of peer and then connect to a random subset of this peer. Like let's say 4 of these peers they connect to, and then they start requesting these 4 for the chunk of files that they have. So while downloading, peer uploads chunks to other peers, right? So we'll see more about how that happens in the later slide. So they may also change peers from which they exchange chunks. They always have to like keep changing. And then peers, they can come and go. So once Alice has the whole file, Alice can either leave the torrent, like she can say that I have the whole file, I don't have to stay anymore, or they can like altruistically remain in the torrent and be a part of this torrent and still be a part of distributing this file to other people who now join the torrent. So this is how it works. So we request chunks, like at any given time, different peers have different subsets of file chunks, obviously. And then periodically, Alice will ask each peer for a list of chunks that they have. And then within that list, let's say I am a torrent, like I am a device, I have chunks 1, 2, 4, 6, 7, 8. Let's say Alice already has the chunks 1, 2, 3, 4. So Alice will request 4, 6, 7, 8, like the ones she doesn't have from me, starting from the rarest one, like the rarest in the network. Also, Alice will send chunks to the 4 peers that are currently sending her chunks, because this is a tit for tat system. Otherwise, somebody who is joining the torrent, they can just take the files and leave. But the algorithm or the protocol of the torrent is set up in such a way that anybody who is participating has to give files and then take files. So as many files they give or as fast they give is the same speed at which they also will get the files. So this works for benefits of both. This works for benefits of both the torrent and the person who is getting the file. So this is called tit for tat when it comes to BitTorrent. So Alice also sends chunks to those 4 peers that are currently sending her chunks at the highest rate. So other peers for the time being are choked by Alice. Alice is not sending data to them. It is only sending data to the 4 peers that are currently sending her chunks at the highest rate. And then every 10 seconds, Alice will reevaluate the top 4 and then find which are the top 4 that are sending her data at the highest rate and put them on the top 4 and send them data. So every 30 seconds also. So the problem with this is why we need this every 30 seconds. Let me first tell you. The problem with this is if we are a part of a torrent and we keep doing this, like evaluate the top 4 who are sending me data and then send them data. Do you understand what the problem might be? If I'm a new person and I'm joining the torrent, who is going to send me data, right? I don't have anything to give to anybody. So I don't have anything to contribute to this tit for tat architecture. So who is going to send me data? So what happens here? So that is why every 30 seconds, Alice will randomly select another peer and start sending chunks, even though they are not sending her anything. So this is how new entries will also start getting some of the data. So this is called yeah, Kevin, you have a question?
Is the new person in addition to the top 4, so it's 5, or is somebody from the original top 4 kicked out of that group?
So good question. So this new person that joins, so there are, let's say, 20 people in this network. So Alice will always choose the top 4 people that she will send the data to. And then when she chooses this person every 30 seconds, then she'll kick out the lowest 4th of her top 4 and give that space to this new person. So she always has top 4 people that she's sending data to. Just that every 30 seconds, she is vacating one of the positions and randomly selecting another person and sending her data. So what happens is this person now, if they also return back the data, they will ultimately become the part of the top 4 on the long run. Otherwise, every 10 seconds when this reevaluation occurs, they will be kicked out and then the actual top 4 will be kept there, right? So this newly chosen pair, if they are sending back this data they're receiving at the same rate to Alice, then they might have the opportunity to join the top 4. Otherwise, they might not as well. So this is how this tit for tat architecture works. So let's see, they have put an image here. So this is Alice and this is, let's say, Bob. So Alice optimistically unchokes Bob. So now Alice is suddenly starting sending data to this random part of the random other person of the torrent who is Bob. And then Alice becomes one of Bob's top 4 providers because Bob also keeps track of who is this top 4 who is giving me file. So once Alice becomes one of Bob's top 4 providers, Bob reciprocates and Bob also sends back Alice data. So on the long run, Bob also becomes one of Alice's top 4 providers until the next 30 seconds when somebody new might join and then Bob might be replaced for that person. So higher upload rate, if you have a higher upload rate, then you find better trading partners who also have higher upload rate and then you get the file faster, right? Because everybody is choosing the top 4. So if you have a higher upload rate, other people are choosing you and then you get better partners and then any file that you get. So this is how BitTorrent used to use people to download files. Like if somebody has used BitTorrent, like you just have to keep downloading them and sometimes you just have to keep the computer, connected until the file is downloaded. And then this is how all these like all the computers that are connected to the network and downloading files, they use like this tit for tat protocol in order to share files. Okay. So this was peer-to-peer applications, right? And we understood why they worked. So in your discussion, you will have to, read the web page that is there and then you can think back to what we discussed today about this, and then you can think about what advantages peer-to-peer has. And also from the article, you'll find some points why it was banned and why some of the peer-to-peer applications had to be stopped. What were the disadvantages? So the next is video streaming and content distribution networks or CDNs. which is a very, very popular thing these days. Like you have Netflix, you have Prime, you have HBO Max, you have Hulu, you have a bunch of content distribution networks around. And we do a lot of video streaming on this. We do it on our cell phones, we do it on our TVs, we might do it on our computers. So we are streaming a lot of video as well. So this architecture is very like evolving at a very fast rate. And if you go to like Google Scholar or other research paper platforms, you'll see that a couple of years ago, like there was a boom of all the research that was happening around content distribution networks in internet, in networking, like all the protocols that people were coming up with, all the problems that people were suggesting solutions on. There is like a huge like outburst of research that was happening on CDNs a few years ago, and I think it's still happening, but a few years ago there was really like a huge boom of this research. So video streaming and CDNs, what are these? So if you look at the internet bandwidth these days, video traffic is a major consumer. Like Netflix, YouTube, Netflix is like 37% and YouTube is like 16% of the downstream residential ISP traffic these days. There are nearly 1 billion YouTube users and there are nearly 75 million Netflix users, right? So the most challenging thing here is the scale. Now that you have so many users, like 1 billion users all over the globe, how do you reach all of them in significantly like fast time, like without very significant delay? This has become a challenge. So a single mega video server won't work, right? Because now you are all over the world and now you cannot have the single video server that might have downtime, that might have delays, that cannot handle this huge load. So you definitely need some kind of scalability. Also, another challenge is the heterogeneity of this video streaming platforms. So there are, like I mentioned, like somebody is watching videos on mobile, somebody is watching videos on laptops, somebody is connected via like their LAN cables to the computer, somebody is watching this on Wi-Fi. So there are different kind of users, different kind of platforms, and also different kinds of bandwidths. If I'm watching a video on the train on my way home from the university, I don't have really high bandwidth because like my cell phone doesn't provide very high bandwidth. But if I'm at home, maybe on my Wi-Fi, I have very rich bandwidth. So there are, even for the same users, there is a lot of heterogeneity depending on what kinds of bandwidths they have. And maybe if I come home, I watch Netflix from my TV. Maybe if I'm on the train, I'm watching it from my mobile. Maybe if I'm at a cafe, I'm watching it on my laptop. So even these platforms that we are watching it from are different. So what is the solution? The solution is to have a distributed infrastructure. First of all, we cannot have it centralized anymore. And also to have it on the application level. Because why? Because the difference now is in the application level, right? It is the data in the internet, the data in the backend, the data in the server is the same. It is now different on how the user is accessing it, right? Whether it is on the mobile phone, whether it is on Wi-Fi or on cable. So now this complexity is closer to the user. So we need an application level solution and also a distributed solution. So what is multimedia? Multimedia, like video, we have a sequence of images that is displayed at a constant rate, right? We have video is nothing but a collection of images that are displayed so fast that our eyes cannot perceive the difference, right, between each frame of image. So that becomes a continuous video to us. So that is a video. And then a digital image is a what? An array of pixels. Like we have small squares that represent a single color or a single property. So that each square is called a pixel. So pixel is represented by a number of bits that might denote what color they are, what property they have. And then the more pixel you have on a screen, the more sharp your screen is, right? So you can have like 1024 by something, 1024 pixels or something like that. So if we have a video, which is essentially a collection of a lot of images, And you might already assume, right, that if I have two images that are like very after one another, and this is a video that my naked eye cannot perceive the difference between these images. So how much difference would these images actually have from each other? Not much, right? So what happens is when people code and send this data, they try to take advantage of this fact that there is not much difference between these images. So first, what do we do when we are sending a fresh image? We do a special kind of coding where we send, instead of sending all the n values of all this purple area, what do we send? We send two things: the color value, which is purple, and then the number of repeated values, which is n. And then if there is black here, we can send the color value black and then the number of repeated value, which is this area. So this helps us in saving a lot of memory and hence saving a lot of bandwidth. And then if I'm going from frame I to frame I plus 1, there is really not much difference. So instead of sending the data of I plus 1 afresh, temporal coding is what? Changing only the difference between these two frames. Like if the leg moved just a little bit, we only send that this is the pixel where the change occurred and this is what the change was. So this is how we can decrease the number of bits to encode an image, and that would help us in utilizing the bandwidth more, because now we have less information to send that we can send actually to, show the whole video. So what kind of encodings we have? We have one called a constant bitrate encoding and other called a variable bitrate encoding. So this is so the constant bitrate encoding firstly is somewhere where the video is encoded into, like if I say I'm sending this video in 2 Mbps speed, I'll send the whole video in 2 Mbps speed. But variable bitrate is actually more interesting. Let's say you are sending a movie and there are parts of the movie where actually something like some intense discussion is happening. So people are just sitting, they are not moving much. So you have that where you can have the encoding rate lowered and then you can send that. And then you have something which is very fast, like people are running, something is changing very fast, and then you can have a higher bandwidth for that and send that using a higher bit rate. So you send more data because essentially more things are changing within the same time frame. So you might need more bits to express that. So that is called a variable bitrate, where depending on the video, you can encode it differently depending on what is happening in the video, what kind of spatial and temporal changes are happening. If it is not much, you can have a lower bitrate. If it is a huge number of changes in a very short span of time, then you can have a more higher bitrate. Okay. So now let's go back to a very basic streaming scenario. What do we do when we are streaming something? We have a client who has an application which they are using to stream this data. We have a video server where the data actually exists, like, or where the video actually exists rather. And then we have the internet, which brings that video from the server to the client. So this is a very basic scenario of how we should be streaming stored video. So what is the protocol that is used mostly on, like, in order to stream video? It is called DASH, which is a dynamic adaptive streaming over HTTP. HTTP we know is the web browser protocol, hypertext transfer protocol. So what does this protocol tell us? DASH. So what it does is, it in the server end, it will divide the video into a lot of chunks of data, right? And each chunk is now stored, encoded at different rates. So if it is, let's say, if I divide the video into chunks such that I have like some place where very slow things are happening, like you're just seeing the maybe background or something. So that is stored as a very low bitrate kind of encoding. And then you have very fast things happening, a fight scene happening or something. And then you have it at a very faster encoding rate. And then we have a manifest file which provides all the, like, the places where these chunks are stored, all the different encoding rates and all the details, those details are all stored in the manifest file. Now what does the client do? the client will periodically measure its bandwidth to the server. Like, what kind of network am I on? Am I on a very high speed network? Am I on a very low bandwidth, like a very weak network? What kind of network am I on? The client will measure this, and then the client will look at the manifest file, and then it will see, okay, so my current bitrate or bandwidth is, let's say, 2 Mbps. So I'll try to request all the 2 Mbps encoding data. So it will ask the server to send it all the data at 2 Mbps encoding. So the server will send it the data at 2 Mbps encoding. And then when the bandwidth goes up, if it goes up like just, with time, then it will again try to choose the other bandwidth rate that now sustains this bandwidth. So consulting the manifest, it will request one chunk at a time, choosing the maximum coding rate sustainable given the current bandwidth. And then it can choose different coding rate at different points in time, depending on the available bandwidth at that time. That is why it is called dynamic adaptive streaming. So this is dynamic in the sense that it changes, like the bandwidth will change, the encoding of the different data will be different. And it is called adaptive because it adapts with the client as the client's bandwidth changes. That is why this is called dynamic adaptive streaming. So here you can see that all the decision making lies with the client. So the intelligence is at the client. So the client is determining when to request chunk. If there is a congestion or something, it will not request. If there is a buffer starvation, like all its buffer is full, overflow will happen, it will not request. The client will determine what encoding rate to request at, higher quality when there is more bandwidth available, lower quality when there is less bandwidth available, and where to request the chunk from. That is, it has the manifest it has the manifest file, so it knows where these things are, where all the servers are. So the client can also choose which server I want to get this data from. Let's say Netflix has a bunch of servers all over the place. So this manifest data also has the details of where these datas are. We'll see in the later diagram. And then the client can choose which is the closest to the client or has higher bandwidth, and then it can choose from there. So let's see how that works. Okay, it is there. Okay, it is there in the later slides. Let's see what they are talking about. So the challenges. The first challenge, how to stream content to hundreds of thousands of simultaneous users. Like, we have a lot of users, and together, like, let's say every night at 8 p.m. everybody is starting to watch Netflix, some movie or something. So you can have hundreds of thousands of simultaneous users that are streaming content. So how do you do that? So there is the very obvious, very basic option one, which is to have a single large mega server. But this comes with a bunch of disadvantages. It comes with a single point of failure. If this server is down, everything is down. It comes with a single point of network congestion. All the traffic is now coming to this server. It comes with the disadvantage of being longer paths to distant clients. And also multiple copies of video are sending over the outgoing link, even though it might not be necessary. Like, so I'm also watching this same video, you are also watching the same video. So multiple copies of the same video are going over the link. So quite simply, this solution just doesn't scale. So what do we have? We have option 2, where we store or serve multiple copies of the same video at multiple geographically distributed sites, or CDNs, or content distribution networks, as we call it. So there are two ways in which this can be implemented. The first is called enter deep way, where the CDN servers are kept deep into many access networks. Like, if I am here, I might see that there is a CDN server like just 2 miles away from here. So this makes it closer to users. So this is what Akamai does. It has around 1700 locations all around the world, which makes any one of the locations comparatively closer to one user at a time. Or the second is called the bring home kind of strategy. Here they have smaller number of CDNs, but a large cluster of them. So you have like maybe tens of CDNs all over the world, but wherever you have it, you call it like a POP, and it is like a very large kind of data center or a very large cluster of data center that is there. It has a very large like bandwidth, it has a very large, you know, storage and everything, but the number of data centers in itself is very small. So this is used by Limelight, who has like smaller number of clusters, but these clusters in themselves are very huge. So now let's see what we were discussing. So CDN, what CDN will do, it will have a bunch of servers, let's say Netflix, and it will store this content at these nodes of CDN. Let's say Netflix stores copies of Mad Men. So these are all its bunch of content distribution networks where all of them have these copies of Mad Men with them. And now I am, let's say, user, and I'm located geographically, I'm located here. So I'm very far from this Netflix original data center, let's call it. So I want to watch Mad Men. So what do? So now subscriber requests content from this content distribution network. So it is directed to the nearby copy from where it can retrieve content. So let's see, these two are the nearby ones, this one and this one. So where's Mad Men? It will go to the manifest to us. It will get back the manifest file, which is just a single small file. It does not take a lot of time because it is just a file. It is not a video. It does not have very high memory. So from the manifest, it knows that this is the server closest to me that has this copy. So I should ask this server to give me this copy. And then if let's say I have traffic here, I as a client can choose to get this copy from somewhere else. Like this is the second nearest server. Let's say this link is very congested. So I'll say that, okay, you give me the copy. So you can see that most of the power here lies on the client. So most of the intelligence, most of the decision, it is pushed towards the client. So this is called over the top, or as we very commonly use the term OTT, right? So we use OTT a lot. So this is how essentially it looks like. So we use internet as a host-to-host communication as a service in this case in order to get these files. That is why it is called over the top of these existing internet host-to-host communication structure. We are getting our video streaming, which it was not originally intended to do. So the term over the top came because originally everything video related you were seeing on the TV, basically on cable, right? So anything that was not cable, that was happening on top of this other technology called internet, which people never thought would be used to watch like cable material. That is why they called it over the top or OTT. So challenges of OTT is coping with a congested internet. So internet was originally, as we all know, not designed for video streaming, right? It was, when in its primary structure, it was designed for data communication, which is not as huge or as time sensitive as video streaming. So the challenges that OTT comes with is coping with a congested internet. So from which CDN node we can get this content, like how your internet will route you towards the proper CDN might not be the most essential decision making when it comes to video streaming. And then viewer behavior in presence of congestion. If the network is congested, how does the viewer behave? Should I, like, if there is very low bandwidth that even streaming is not possible, what do we do? Do we try to find a different link? Do we try to find a different server? Do we try to cache something? And then what content to place in which CDN node is also a very important question these days. But this also has a lot of, I won't say research, but a lot of analysis that goes on. Like, let's say I have a server near my house that Netflix is operating. It is not possible for Netflix to store all of their, all of the data they have, all of the videos they have. It is not possible for them to store everything in every single server around the world. So they have to make this very calculated and very, important decision of which content to place on which server. So they do it in a number of ways, like, depending on who is watching what most in an area, if somebody is requesting something for the first time, trying to cache it, and they do a lot of like protocols that they follow in order to do that. But this is again never a very optimum thing. So a user might always request something. There is always a chance that a user might request something that does not exist in the nearest server, and it might take time for it to get to this first user. But once this user has requested it, if any other user wants to get it, it is then stored in this local cache. So there is still some kind of discussions on what content to place in which content distribution network node. Okay. Okay, so let's take a closer look at this CDN content access network. So let's say Bob is a client and Bob is trying to access a video with the URL http://netcinema.com, and then they have this identifier. But this video obviously is not stored at this NetCinema website. It is stored in this server, which is called King CDN Content Distribution Network server. And this is the location for the video, right? So this is Bob. This is Bob's local DNS server. This is NetCinema, which is this URL. This is NetCinema's authoritative DNS server. Then we have King CDN, which is where our content distribution network is. And then this is King CDN's authoritative DNS. So this is where we start from. We have all the places that we might need to visit. Now let's see how the actual workflow proceeds. So first, Bob gets the URL for this video called netcinema.this from this NetCinema webpage. Like it might say that visit this website for, like, you can think of this as netflix.com something something, right? So it gets this website from the netflix.com webpage. Then Bob will go to its local DNS server and tell me where is this netflix.com, this thing, what is the IP? Give me the IP. So the Bob's local DNS server will contact, like it might be hierarchical or it might be direct, but it will contact Netflix Cinema's authoritative DNS server and get back the URL for this video, right? So when you get this video, you get, like, when you query the DNS server, it sends you the canonical name, right? If you remember our discussion, so this might be the alias name and this might be the canonical name stored in the DNS record. So it gets back this. What does it do then? It tries to find where this website lies. So it goes to the King CDN's DNS server and asks it, where is this? Give me the IP address of this. Now, after we get the canonical name, now here, this is the actual name. So this will get it back the actual IP, like 10.0. something something something, it will send it. So once it sends it back the IP, Bob can access this using the IP, and then this is streamed via our dash using HTTP. So this is how a content access works. Like you can see, like you have this Netflix website where you get the IP for the Netflix video. Bob asks his DNS server, get me the IP for this Netflix video. It tells that, okay, you don't need IP first. This is an alias name. So you first need the real name or the canonical name. So this is the canonical name. And then it sends it back. So it now asks the server, this is the canonical name I have with your domain. What is the IP? It gets back the IP. It sends this IP to Bob. Bob requests the video from that IP, and then it gets streamed via HTTP. So this is how a content delivery will work. Like this is what happens in the backend when you are trying to watch a video or a movie on Netflix. So like I said, so they did the same case study using Netflix. So what it is doing is, Bob is the user. Bob has a Netflix account. So first Bob will log in using his Netflix username and password. So Netflix will do the registration. It will try to, do all the authentications, and it will give him the access. What will Bob do next? Bob tries to browse a Netflix video. So this Netflix video is stored somewhere in the Amazon cloud, some physical server somewhere. And then there are a lot of multiple replications of the same server, right? So when Bob requests for the video, the main server will send back the manifest file that these are the servers where this video exists. Please find whatever is suitable to you and please ask for the video. Now when Bob has the manifest with all the details, all the URLs for, and all the IPs for all the servers, Bob will find the one closest to it in a non-congested link and then ask that server to send it the data, and then a dash streaming connection will start. So this is how what happens in the backend when we are trying to watch a Netflix movie. Okay, so before we go to socket programming, let's take like a, let's say 10 minutes break. So we'll start at 7:10 again. Okay, let me share that. Okay. Okay. So now we move on to socket programming with UDP and TCP. And this is another aspect that we can by ourselves on Python or Java. We can try creating a client socket and a server socket by ourselves and then try to do like fun stuff with it. I'll see if I can like incorporate one lab with this later, but let's go over what socket programming is first. So, okay. So socket programming, why do we need to learn socket programming in networking? Because it is very a baseline on how to build client server applications that communicate using sockets in the application layer. So this is not just like a lab, it will also like give you insight on how sockets work in real time, like in a very simple way. So socket, as we know, is the doorway between application processes and the rest of the end-to-end transport protocol. So it behaves like a gate just between this application level process, which is controlled by our app developer and which is interacted most by the user. And then the rest of the network layers, which is controlled by the OS and which flows through the rest of the network. So there are two socket types for the two transport services that we have. So the first is UDP, which is called User Datagram Protocol, which is a kind of transport layer protocol. And then the other is TCP, which is reliable and byte stream oriented, which is called Transmission Control Protocol, which is the other kind of transport layer protocol. So there are two main transport layer protocols that we'll learn about in the next chapter. But for this topic, the important thing to know is that each of these two transport layer protocols, they have two different types of sockets that you need to set up for them. So what is an example that we can have of very simple server client communication? Let's say the client reads a line of characters from its keyboard and then sends this to the server. And then let's say the server is a server that has the function of converting whatever it gets to uppercase. So the server receives this data from the client, converts the character to uppercase, and then sends back this modified data to the client. So the client gets this data and displays it on the screen. So this is like as you can imagine, a very simple example of what happens in real life client server applications. Like if you request a website, the server sends you the website and you see it on your browser. So similarly here, what we do when we are trying to replicate it using our IDE, we create a server program, we create a client program. The client program, when we run it, we send something written in, let's say, lower characters, lowercase to the server. The server, who is perpetually on, like who is always on, right? So they get this request from the client, it converts these characters to uppercase, and then it sends this data back to the client. The client displays it on the console, and we are done with this communication. So what happens? We start with UDP. UDP has no connection between the client server. UDP is like a best effort protocol. It will just send the data out there and forget about it. Whether it reached your server or not is not a concern to UDP. So there is no handshaking or connection happening before sending the data. The sender explicitly attaches the IP address of the destination and the port number to each packet and then sends it out there. The receiver will extract the sender address and the port number, and then it will do the modification and send it back to that IP address and port number. So for UDP, transmitted data might be lost, it might be received out of order, and there is no way to know because UDP doesn't care. It just sends it out there. So from an application viewpoint, UDP provides unreliable transfer of groups of bytes, which we will call datagram, between the client and the server. So let's see a socket interaction, how it happens. So a server is a perpetually on server. It is always on. So let's say it is running on server IP. We create a socket in the server when we start it, and then we have the server socket. And then we start our client where we create a client socket. We create a datagram, the whatever we want to convert from lowercase to uppercase. We create the whole datagram with that data with the server IP and the port. Here we see that the port is X for this specific server process. So we put the server IP, we put the port, and then we send the datagram to the server via the client socket that we just created. What happens? So we have this socket in the server, which is always on. It receives this data from the server's data from the client, which was addressed to it. So it reads this data. It does whatever it needs to do, like converting to uppercase, whatever change it needs to do. It writes the reply, appropriate reply, and then sends it via the server socket to the specifying client address and the port number to back to the client. And then this client will read this reply of this datagram from the server. It will do whatever it wants to do with it, like display it somewhere or something. And then it will, once it is done with all the functions, it will close out the client socket. The server socket remains on for any other request that might come from any other client, right? So this is how a basic flow occurs in UDP. We don't need to create a dedicated connection. We just need to open a socket. We need to put the server IP and the server port, and then we need to send the data. And then we get back the reply from the same socket. Once we are done, we close the socket. This is the example of the whole code that we do for a UDP client, like the client side. So we are having a socket library. We are importing this. We provide the server name, whatever the server host name is. We provide whatever port the server is. So let's say if this was HTTP, then this would be 80. So we provide whatever port the server is using for this service. We create the client socket. And then this is the message, which let's say I'm asking from the user to put the message saying input lowercase sentence. Once we have this message here, we send this message to via the socket, and we put the server name and the server port here, and we send this message out. Once we send it out, next we will get the modified message and the server address in our client socket back. We get it as 2048 byte packets. And then we print this if we want to print it. If we have encrypted it or encoded it, we will decode it and print it. And then we close out the client socket. So this is a basic, very simple UDP client socket that we can have. So the corresponding UDP server program we'll go in a bit. Let's see what they are explaining. So we include the Python socket library, which has all these socket commands in it. So we create the UDP socket for the server here. We get the user input from the keyboard via this input method, and then we put it in this message variable. We will attach the server name and the server port, and then we'll send it via the socket we had created. We will read the reply characters from our socket that we get back, and then we put it into a string with this specific byte size. We will print out this received socket, and we will close out the socket. We are done. So now the similar server for the UDP will look like this. So we have the socket library that we need to import at first. We have the server port that we define, which if we are creating our own server, we have a range of ports that we can choose from. Otherwise, if it is a previously defined server like HTTP or something, it has a specified port that you have to put. And then you create the server socket at the first, and then you bind this to the server port, which is this one, and then your socket is on. The server is ready to receive, it is on. And then you have this while true here loop. That means that it is like on every time, like all the time when it is true, it will keep listening. And then you get the message from the client. You get the client address, and then you get the server socket. You get the message in 2048 bits. You modify the message, whatever this message was, you modify it, and then your modified message will be like you decode it, and then you convert it into upper cases, which is what we defined for this server. This server converts sentences from lowercase to uppercase. So we decode it, we convert it to uppercase, and then we use the same socket, the server socket, to send out this modified message. And then we had the client address, so we send it out there to the client. So similarly, here we have the UDP server socket. We bind it to the local port number, which we give, which is 12,000. We open this loop forever because the server is always listening. So this is a forever loop. We read from the UDP socket that gets the message from the client. We get the client's IP address and the port number also. And then we use that to send back this uppercase string to the client. So now this was UDP. We did not need to maintain any connection. There was no handshaking. We were just sending the data with the socket and send and forget. So, but for TCP, we need to set up a connection first, and then we need to send this data. So the client must contact the server. The server process, as in UDP, it should first be running. The server should have created a socket that welcomes this client's contact. So the client contacts the server by this time creating a TCP specific socket. So we mentioned there are two types of sockets that we can create. One is a UDP socket, which we went through in the previous example. Now for this, we need to create a specific TCP socket. And as expected, we need to specify the IP address and the port number of the server just for this socket, because we need to dedicate this socket to this communication between the server IP and the server port. So when the client establishes this, creates this socket, client TCP establishes connection to the server TCP. So now it is not just sending and forgetting. Now I have a connection between the client and the server. So similarly, when contacted by the client, not before that, when server is contacted by the client, server TCP creates a new TCP socket for this server process to communicate with that particular client. So now the difference here is that here both of them create sockets that are dedicated to this communication only. So this allows the server to talk with multiple clients at a time, because now the server can create a different socket for each of the clients. It just doesn't need to have like one perpetually on socket where it is listening. It will create socket as needed for each communication. And then source port numbers are used to distinguish clients. So we'll learn more about this in the next chapter, how we use source port numbers to distinguish each of these connections. So from the application viewpoint, TCP provides reliable in-order byte stream transfer between the client and the server. So with TCP, if you send data, you will know if the data has reached your destination or not. You will also, like if you break your message into packets and send them, at the destination side, it will be arranged as like the packet was before it was broken down. So you get reliable. If it was not delivered, TCP might like re-request you to like the client to send the data. So it will provide a reliable transfer and an in-order byte stream transfer between the client and the server. So this is the advantage of TCP in most cases. So how does this socket interaction work? Let's see. So here the server is there. So the server creates a socket and a port X for this incoming request. And then it waits for the incoming connection request, whichever client is gonna ask it to connect with them. Now the client wants to connect with the server. So the client creates a socket, connects to this host ID, whichever is the ID here, the port X, which is the port for this server, and then it creates this socket. Now when this socket is created and this connection is requested, this will set up a TCP connection. Here we'll see later how the code actually looks like. And then the client will send request using the client socket. The server will read the request, do the modification, whatever needs to be done, and write the reply back to the client. Now the thing is that now it does not need to close out the socket. If it has more things to do, it can use the same connection to again send some request. It will do the same thing, it will reply. This will go on as long as the client has something to say. Once this is done, the client will close the socket and the server will also close this socket. It will open any new socket for any new connection request that comes its way. So this is how TCP functions when TCP is used for a client server socket interaction. So let's see the codes now to better understand how it happens. So first we look at the TCP client code. So we have the same socket library that we import. We give the server name, whatever the server name is. We give the server port, whichever port number the server is using. Then we create a socket. And then we start a connection, TCP connection request with the server and the server name and the server port. So this time we initiate a connection first before just, sending data via the socket using the server name and the server port. This time we first try to set up the connection. So once we have the connection, we will take the sentence from the user. Let's consider this is the same scenario. So we take the lowercase sentence as input, we encode this sentence, and then we send it out via the client socket that we have created. When we get back this modified sentence, like the uppercase sentence from the server, we get it back. We print something out, like if we want to print it out to the user after decoding it, and then we close out the socket. So this is how the client works. Now let's see what happens on the server end that is different from before. So like in the client, as we can see, we create a TCP socket for, the server and the port. And then we don't need to attach the server name and port number when we are sending out the message, because this socket itself has the property and it itself has the connection of the name and the port. So we don't need to put it here. So now the server. So what happens in the server? So the server has this port number. The server creates this socket and then it binds it with its port number and then it is ready to listen. It has this listen mode on. So now what happens? Now when there is a connection request from the socket with a client address and the server request and the server socket wants to accept it, it will send back the accept method and then it will send it back via the client socket. So when the client gets it, it knows that the handshake has happened. The server has accepted this connection request. Now I am ready to send it. So it sends data to the server. The server receives this data using this connection socket. It decodes this data. This is the sentence. So it converts this sentence to uppercase. It gets this capitalized sentence. It sends out this capitalized sentence via this socket, encoding it. So now if there was anything more, there would be more lines here. Like there would be more things happening here. If there is nothing more happening here, or if it is like just going back, it will just keep looping here. If there's nothing more to do, but if there is something more that the client sends, like convert this sentence also. So this will again go here and it will start looping here. Once the client has sent everything and the client has terminated the handshake, the socket here in the server end will also close. So we'll know more about how this connection happens, what this handshake is later when we go over TCP communication, like TCP in the next chapter, we'll know more about how this communication is set up and how this communication is tiered down. But for now, we set it up, we do whatever we want to do, we keep sending until we are done, and then we close both the connections. So let's see what they explained. So we create a TCP welcoming socket, which is the main socket which stays on, and then the server begins listening for incoming TCP requests, which will loop forever. It will keep listening. And then server waits on accept. If there is a new incoming request comes, then a new socket is created just for that request, which is called the connection socket here, just to distinguish it from the server socket so that you don't confuse the two. This is a different name. So this is where the server socket accepts this TCP connection. The TCP connection that has come here, it accepts it and it moves on to do the rest of the communication. It reads bytes from the socket, but there is no address like in UDP because you already have the connection set up. So you don't need the address for the client here. And then you close connection to this client and then you're done, but you don't close this while loop. So you still have your server socket open. So now if another client wants to connect, then the server is still listening. So now if another client wants to connect, it will be another connection socket, like let's say connection socket 2, and then this will happen all over again, and then this will keep happening for every request that the client gets. For every request, it will be a separate connection that is set up and that is toned down. So we see that in our this chapter, what did we complete? We completed application architectures, what client server architecture is and what P2P architecture is. We completed application service requirements like reliability, bandwidth, delay. We completed internet transport service model, what is connection oriented and what is not connection oriented, which is UDP. We completed a few protocols in the application layer like HTTP, SMTP, POP, IMAP, DNS, peer-to-peer like BitTorrent. We discussed over video streaming and content distribution networks. We discussed socket programming using TCP and UDP sockets. So this is the application layer. So most importantly, we learned more in depth about what an actual protocol is, like how typical request and reply messages work, the client requests information or service and the server responds with a data or a status code. We learned more about that in a message there is a header which gives some information about the data, and there is the actual data, which is the actual payload that is being transmitted. We learned about control and messages, centralized and decentralized. We'll go over each of these concepts in more detail in the later protocols as well, because you'll also like encounter many of these like stateless versus stateful, reliable versus unreliable. In most of the later protocols also we'll come across these terms and we'll discuss why they are, how they are. And then we also came across this term of pushing the complexity towards the network edge. Like any complex algorithm that we need to implement, any complex kind of software that we need to implement, we always try to do it towards the edge of the network, like where the end systems are, like the user or the server. We always tend to put all the complexity towards the end, and we keep the intermediate part of the network very simple. We try to keep it more simple so that there is no calculation or decision making, more complex decision making at the middle, so that the delay is minimum. When a packet is already in the network, there is no complexity there. So we try to push all these complexities, any new protocols that might come up tomorrow. The urge of the network engineers would be to push the complexity of this new requirement towards the edge and keep the network as it was before. So this also is an important theme that we went over. Okay, so let's move on to the next chapter actually. Let me find it. Okay. Let me share. Okay, so if we remember our layers of the internet, we know that we had application layer, and then we had transport layer, and then we had network layer, and then we had data link layer or link layer, and then we had the physical layer, right? We had this 5-layer distribution for the 5, and then when we had the 7-layer, we had application layer divided into session, presentation, and application. So if we consider the 5-layer architecture, we have physical layer starting from the very bottom, then we have the data link or the link layer, then we have the network layer, then we have the transport layer, and then we have the application layer. So we completed, so we went over the main points of the application layer. So we move on to the next layer coming from the user to the bottom, which would be our transport layer. So in this chapter of transport layer, Our goal would be to understand the principles behind these services, which include multiplexing. Multiplexing is like combining something coming from a lot of channels into a single channel, right? And then we have demultiplexing, which is taking the single channel data and distributing it into all those multiple channels that it was coming from. So we'll understand more on multiplexing and demultiplexing. We'll talk about reliable data transfer. That is when we are sending data to somebody, how do we know that this transfer is reliable? Do we get to know that our data reached the destination? Do we get to know if it got in the way? Can we resend it? So all this comes under reliable data transfer. Then we have flow control, like the flow of the data packets, like the order in which they go from one place to another, how they go. Like if I'm sending 4 packets at a time, if I'm stopping, like for example, if the receiver is not able to process data as fast as I'm sending them, I need to slow down. So that comes under flow control, which also we'll discuss. We'll also talk about congestion control. When the network is congested, how do we get to know it? Do we get to know it? Can we stop sending data if the network is congested to help, alleviate the problem? So we'll talk about that also. And then what will we learn? We'll learn about the Internet Transport Layer protocols, which is mostly 2 protocols that exist. The first is UDP, which is a connectionless transport protocol, and the second is TCP, which is a connection-oriented reliable transport protocol. So TCP, we'll also learn about congestion control in TCP. So TCP can do some congestion control functionalities. We'll also see how it does that and what benefits it provides. Okay. So here is our roadmap for this chapter for the transport layer. We'll look into the transport layer services, what services the transport layer provides. We'll look into multiplexing and demultiplexing. We'll look into UDP. Then we'll look into the principles of reliable data transfer, why UDP doesn't work in some cases, why we need TCP. Then we'll talk about TCP. We'll talk about congestion control and how TCP implements congestion control. Then we'll talk very briefly about the evolution of this transport layer functionality, how it evolved to be where it is today. So transport layer services and protocols, what do? They provide a sense of logical communication between the application processors and the different running hosts. So you have the applications that you as a user use. So it provides a sense of logical communication between these different application processors. Like if I am a web browser and you are a web server, it provides a sense of a logical communication between the web server and the web browser. Everything that happens in between, running on different kinds of hosts. So this is how it happens, right? So you have transport layer here, and then you have transport layer in the end system, which here is the server. So if you remember what we talked about when we talked about routers and switches, we said that routers are mostly layer 3 devices, and then switches are mostly layer 2 devices. And then you can think of all our cables as merely layer 1 device. What that means is that cables, they will pass all the physical data. Switches, they can see the physical data properties and the data link layer data properties. So they can access these two and they can modify these two. When we go to routers or layer 3 devices, we can access these 3 layers. So we can access the physical layer, we can access the data link layer, and we can access the network layer. So the transport layer is not touched by the devices in between, like the intermediary devices. They are mostly layer 2 or layer 3 devices. So that is why a transport layer is a logical end-to-end transportation. That is, it starts from the end user where it is modified, and then it reaches the destination end user where it is received and modified. So that is the communication it is between. So the transport layer protocols, what happens? So the sender at one end, they will take this application layer messages from the top, they will break it into segments, and then they'll pass it to the next layer below them, which is the network layer. So the receiver will do the same thing in opposite order. The receiver will take the messages that come from it to it from the network layer. It will reassemble these segments into messages. It will pass them over to the application layer or above them. So this is what the transport protocol on an overview does. So there are two transport protocols that are available to internet applications these days. And then if you are creating an internet application, you get the choice between these two depending on what you are going to do. So these two protocols are TCP or Transmission Control Protocol and UDP or User Datagram Protocol. So here they give an analogy of a household. If there are like 12 kids in Anne's house, they are sending letters to the 12 kids in Bill's house. Then you have the houses, which are the host or your laptop, you can think. And then kids, which are the processes or the actual applications like your email server, your file transfer server, which are actually sending the messages. And then the app messages are these letters in these envelopes. So this is the analogy. Your host or your computer is the house which houses a lot of different kind of processes, which are your application layer processes. And then transport layer protocol is Anne and Bill, who will actually, get all this bunch of letters and they'll try to get it to each of the kids. So when the kids in Anne's house write the letters, Anne will take all the letters from these 12 kids. So that is called multiplexing in a sense. And then they will send it out through the postal network. And then the postman or the postal network will deliver this 12 letters to Bill's house. And then Bill will segregate these 12 letters based on each kid, which you can think of as the demultiplexing. And then he will give them to all the siblings, right? So this is how they have drawn the analogy of what transport layer is supposed to do. So the transport layer essentially is the communication between these processes. So the processes will rely on, these will rely on and enhance all the network layer services below them. Okay, so the network layer is below this transport layer, which will actually provide the communication between these hosts. So the network layer protocol you can think of as the postal service that actually will take the letters from this house to that house. This is actually a very good analogy because when we go to the other layers below the network layer also, we can draw analogy with the postal service of those layers, right? So the network layer you can think of as the postal service, which decides about taking the letter from one place and giving it to another place, right? And then when we go later to the other layers, we'll see how, like when we go to the network layer in more detail, we'll see that there is this protocol called Internet Protocol, or as we have all heard about it, IP as it is called. So when we go to IP, we'll see how like routing works, like how when Anne is sending the letter to Bill, how does the postal network decide which path to take? We'll discuss all those when we go ahead into the network layer. So let's move ahead. So for the transport layer, what does it do? So there is a sender and there is a receiver. So sender is passed an application layer message. So the application layer via the socket will pass this message to the transport layer. Then the transport layer will add its own header values with certain details like which process it is coming from and all that, like the port number, etc. And then it will send this out to, it will divide it into segments and it will send it out the segments to IP layer. So this IP layer will get this and this IP layer will pass it. Like we'll see later how IP layer adds its own header and everything and passes down. But for now, let's think this IP layer passes this message to via the network to the receiver. And then when the receiver gets this message, it is again passed up via all these layers to the transport layer, who receives it and takes this segment, removes this header, which is, it checks all these header values. It tries to see if this is proper, if this is correct, if the packet was not modified, and then it removes it and it sends it back to the application layer. So it demultiplexes it and it sends it back to the appropriate application process it should go to. which is called demultiplexing. So now there are two principal internet transport protocols, as we mentioned. We have TCP, which is called Transmission Control Protocol. It is reliable. It does in-order delivery. That is, it can rearrange the packets when it reaches the destination in the proper order. It does congestion control. It does flow control, and it requires a connection setup in order to function. Like there needs to be a connection established before we can actually do the packet transfer. The next is UDP, stands for User Datagram Protocol. It is unreliable. Once we send it, it is like derived from, we'll go later. Yeah, so it is derived from IP, which also has this best effort, kind of way of working. So best effort is I'll do my best to send it out, then I don't know what happens to it. So that is why this is unreliable, because you send it, you don't know if the destination received it or not. And then it is unordered. If I send packets 1, 2, 3, 4, if packet 2 gets delayed and packet 2 reaches the destination after packet 3, there is no way in UDP to tell that this is packet 2, this should be placed before packet 3. But in TCP, there is. So this is unordered delivery. And then this is a no-frills extension of the IP, which is also a best effort protocol, as we will see in the later chapter. So these are the two protocols that are available to us in our transport layer, which if we are creating an application, we need to decide which protocol we need to use. So both of these, this is very important. Both of these protocols, they cannot guarantee us delay, how much delay will be, like a minimum delay, maximum delay. They cannot provide any guarantees, and they cannot provide any bandwidth guarantees. How much bandwidth my data will get on the media, nobody can guarantee that. So TCP and UDP, they cannot guarantee delays and they cannot guarantee bandwidth. So now let's move on to multiplexing and demultiplexing. So as we mentioned, multiplexing is putting together a bunch of messages from the same source, a bunch of messages from different processes, putting it together, sending it out. And then demultiplexing is getting this data from different processes, segregating it to which process it should go to, and then sending it there. So in this diagram, we see that this yellow boxes are sockets, and then P1, P2, P3, and P4 are 4 processes that we are talking with. This laptop and this laptop can be thought of, sorry, these are desktops. These desktops can be thought of as 2 clients. This is a server, let's think. So the server is encouraging connections from these 2 clients. So what happens? So this P1 has a conversation with P3, P2 is having a conversation with P4. But this application, you can see that the processes are different, but this application is the same. Like you can think of this as, let's say, a HTTP server. So the server is the same, but the processes are different. So when the sender, let's think of the server as the sender. So when the sender is multiplexing, it handles data from multiple sockets, these 2 sockets here, adds a transport layer to each of these, which will later be used for demultiplexing here, and then it sends it out. When this same device, when the same transport layer acts as a demultiplexing device, it gets back packets or messages from both of these processes. It uses this header information to decide which process it should go to, and then sends the proper packet to the proper process. So this is how demultiplexing works when it is receiving back data. So let's see. Let's say we have a client who is using Skype and Netflix, and then the Netflix is hosted on this Apache HTTP server. So the HTTP server will take this message from the process. It will add this transport layer header to it. And then it will, like when it goes down, as we mentioned, each layer will add its own header, encapsulating the rest of the message. That again, this header will be used in the appropriate layer when it goes to the receiver. So the network layer adds its own header, and then it goes out, it reaches the client. When it reaches the client network layer, the network layer will check this header, see if everything is okay, and then strip away the header, and then provide the rest of the packet here, and then give it back this HTTP message. So now how does the transport layer know which message, like the message, whether to send it to this browser, whether to send it to Netflix, or whether to send it to Skype? How does it know how to distinguish that? So this is why the demultiplexing property of this transport layer is important. So when it goes to the transport layer, we'll discuss how it decides that. But for now, let's see that it demultiplexes the data and it provides the data to the appropriate application that it should go to. You can think of demultiplexing as when we take proper exits on roads, right? Which road we need to go to. So multiplexing similarly, where the transport layer gets these packets from a bunch of different processes running on a bunch of different applications, and it modifies them, like it adds its own header to them to distinguish it later, and then sends it out the system in the same way, in the same channel that every other data is going through. So this is called multiplexing. So the transport layer gets all the packets from all these applications and it sends back down in the same channel that every data will go through to the internet. The rest of the network doesn't need to know that these three came from different applications. It just goes through as it came from the same host, which is the same device. So this is like an analogy of multiplexing, where like a lot of entries come to the same highway and they can go forward in the same route. So how does demultiplexing work now? So host receives IP datagrams. So IP is the layer below, right? You know, the network layer. So the host receives these IP packets. So each datagram will have a source IP and a destination IP. So if it is coming to me, it has my source IP address. So, and they also carry one transport layer segment, the one within it. So each transport layer segment, they will have a source port number and a destination port number. So now we have a source IP or destination IP, so that the letter comes to the house, right? The Anne's letter goes to Bill's house because they have Anne's source IP address, and then Bill's destination address. But now when you take out the envelope, which is the datagram, and you get the transport layer segment inside, which is your letter, you see that there is a name of each sibling on it, right? The name of the person to which this letter is addressed. So that is called the destination port number. And in the bottom, you also have the name of the person who wrote the letter, which you can think of as the source port number. So now, in addition to your source IP and destination IP, you have the source port and the destination port also. So the host uses these IP addresses and port numbers to direct the segment to the appropriate socket, which has that IP port number combo. So you have the source port, destination port, and other fields. So you use these two to, basically the destination port number and the destination IP address to decide where this should go. So when we are doing connectionless demultiplexing, which is the case for UDP or user datagram protocol, remember that when creating socket, we specified the host local port number also in the socket, like which port this socket is going to talk to. Like this way, datagram socket, my socket 1 is equal to new datagram socket going to port 12534. So this is the host local port number. So when creating a datagram to send into a UDP socket, which is our connectionless socket, we must specify the destination IP and the destination port in the datagram socket so that it knows where it needs to go. So when the receiving host receives this UDP segment, it checks the destination port number and then it directs this UDP segment to the socket with that port number. So if I have 12534, I go to the destination IP address, and then there are, let's say, a bunch of processes, 12534, 12000, 12101, and then I see that the port number here is 12534. So I forward this packet to that port, like the socket with that port number, because sockets have port numbers, as we know. So the IP UDP datagrams with the same destination and port number, but different source IP addresses and source port numbers, will be directed to the same socket at the receiving host. So this is again important, that since in UDP it is connectionless, right? So we'll see how this is different in TCP. But in UDP, since this is connectionless, if I have a letter that is going to the child A in their house from me, it will also be directed to the same socket. If it is going from you to the same process, it will also go to the same socket. So the socket is destination specific in connectionless demultiplexing. So the server or the destination, they have a socket. Everybody who wants to send data to that socket will send it to that socket. In TCP, the difference is you don't have a combination of a port number and a destination IP for a socket. You have a combination of all four things. You have a combination of the source IP, source port, destination IP, and destination port. So you have a socket there for each connection that is happening. In UDP, you have a socket for each destination process. So any connection, any message that is directed to this destination process, it will go to the same socket. So this is a connectionless multiplexing. So let's say we have an example here where we have two end users and we have the server. So I have created my socket using my port which is 9154. This user has also created their socket using 5775. And then here the server has the socket 6428. And then everyone is trying to talk to this server. So when A is sending this packet to this server, A will send this packet to this socket with this destination IP and destination port. And then it will return back, it will send it back data using the destination port number as 9157 now. Now, when P4 has to communicate also, P4 will use the, like when P4 is communicating with P1, the source port number will be the same 6428. The destination port number will be 5775. So that when the server replies, it uses the same socket to send out the reply, but to this destination port. So let's see. Yeah, so this is the difference. So here it is the same socket. Let me try to go forward if I can get an image. See, here it is the same device with the same application process, but here there is different sockets for each of the processes, even though the application is the same. So this is the difference. We'll go into it in a bit, but for now, let's see. Here we have the same socket for the same application process for multiple connections, for a connection, for multiple requests, connectionless demultiplexing. So we'll start next class with connection oriented demultiplexing and we'll continue from there. So any questions up till here? Okay. Yeah, sorry, go ahead. Go ahead.
I was just saying no questions.
Okay. Okay. If there are no questions, then that will be all. Thank you. And in case anyone missed it, from the next week, we'll not have our defined office hours, but rather we'll do an office hour by appointment where if any of you have anything you like to discuss with me, anything you want to pass by me, just drop me an email or a message and then we can set up a time within the next few days that works for both of us. Like it might be after office hours, it might be like any time that is for both of us.
Thank you.
Thank you.
Have a good weekend.
Thank you. You too.
Thank you.
Thank you.
Thank you, Professor.
Thank you.